This is Chen Chen. In this presentation, I'll be introducing our work, Audiovisual Navigation in 3D Environments. Embodied perception is a multi-sensory experience, but we often use vision, audio, touch, and smell to move around in the environment. But today's embodied agents are deaf. Motivated by empowering the agent to hear, in this work, we introduce audiovisual embodied navigation. We define the audiovisual navigation as an agent navigating to a sounding object with vision and audio perception. In this figure, the top-down map is overlaid with the acoustic pressure field heat map, where the gradient of the field reflects the geodesic path the agent needs to take to reach the goal. To achieve this goal, we first introduce sound spaces, an audio simulation platform to enable audio-visual navigation for two visually realistic 3D environments, Replica and Matterport 3D. Our audio simulator produces realistic audio rendering based on the room geometry, materials, and sound source location. The platform can play varying sound of your choice in real time by pre-computing a transfer function between locations. Now let's see an example of an agent navigating to find a ringing phone in our simulation. Wear your headphone to perceive the binaural sound. Notice how the direction and intensity of sound change as the agent moves. Here we show you another example of our simulation where a user navigates in a large environment of Matterport to locate the piano. In the standard point goal task, the agent receives a GPS signal from the goal to navigate, which is a displacement vector in the form of delta x, delta y. We propose two new tasks. The first one is audio goal, where the agent receives an audio signal from the goal. This captures real-world scenarios where a target initially auto view makes some sounds. For example, baby crying and dog barking, and the agent must move to find it. The second task is audio point goal, where the agent receives both an audio and a GPS signal from the goal. This task augments the point goal navigation task and captures scenarios where the agent has a GPS pointer towards the goal, but should leverage audio-visual cues to navigate in unfamiliar environment. And all agents have visual perception and do not know the environment or the map beforehand. We also generalize a state-of-the-art RL model to accommodate audio observation, which is represented as spectrograms of left and right ear waveforms. Inputs are first encoded by CNNs, then fed into recurrent neural network and subsequent actor-critic networks. The agent executes a movement action sample from the policy distribution, and the environment sends the observation and reward feedback to the agent. During training, the agent is rewarded for navigating efficiently to the target. Now let's see a qualitative navigation example of audio point goal agent looking for the ringing phone. In this case, the displacement vector tells the agent the goal is in the diagonal direction, so it can either first go straight or first go right. But by leveraging the direction cues in audio, the agent immediately knows the sound comes from the left side of the bed and should first go straight and then right. In comparison, point goal agent performs much worse because it is confused whether it should go straight or go right and gets stuck behind the bed. Audio goal agent figures out the sound comes from the front much quickly than the point goal agent, but since it doesn't have the displacement vector, it goes all the way to the other side of the room. An audio point goal agent takes almost the diagonal shortest path to reach the goal. To understand the difference of those agents, we need to study a few questions. The first question we want to investigate is, does audio help navigation? To study this, we evaluate the impact of adding audio sensing to visual observation by comparing point goal with audio point goal agents. And we adopt the standard navigation metric SPL for evaluation, which is success weighted by inverse path length. The bar charts plot the performance of each agent with different visual sensors on two datasets, from which we can see that audio point goal agent performs much better than point goal agent by leveraging audio cues, showing that audio improves accuracy significantly. Next, we explore the extent to which audio supplies the spatial cues available from GPS sensing during audio-visual navigation. This test requires comparing point goal to audio goal, as we know the GPS noise or localization error often accumulates as the agent moves. In these two figures, we plot the performance of each model under audio noise and varying degrees of GPS noise. We see that audio is by definition immune to GPS noise and is very robust to microphone noise. Furthermore, audio point goal degrades much more gracefully than point goal in the face of GPS noise. This is a key result. This is evidence that audio signal gives similar or even better spatial cues than the point goal displacements, which are likely overly optimistic given the unreliability of GPS in practice and especially indoors. While in the results so far, the agent was only hearing telephone sound and searching for it. Here we train and test our audio goal and audio point goal agents with 102 sounds, including telephone ringing, engine sound, music, and etc. Note that all test environments are unseen. While the performance of audio goal agent declines as the sounds become more varying and unfamiliar, it still achieves quite decent performance. And we can also see that audio point goal agent almost always outperforms audio goal agent due to the extra displacement vector information. To examine if our audio goal agent learns meaningful feature from input audio, we perform t-SNE projection of audio features. The color transition from blue to red in the angle plot shows the direction of the goal moving from the left to the right. And blue to red gradient in the distance plot shows the goal from being close to being far away. And this indicates our learned audio goal feature has a strong correlation with the ground truth information. We expect that the audio and visual input vary in their relative impact on the agent's decision making based on the environment context and goal placement. And here we show the importance of vision and audio in selecting the action, highlighted by red and blue boxes respectively. Initially, the agent uses vision to recognize free spaces in front of it and moves forward. At this moment, it relies on audio to tell the goal is on its left and decides to turn left. Finally, the agent decides to stop because the sound intensity has peaked, and here audio plays the most important role. In conclusion, in this work, our main contributions are: we first introduce the task of audio-visual navigation by autonomous agents in complex, visually and acoustically realistic 3D environments. We generalize a state-of-the-art RL model to accommodate audio observation and demonstrate its impact on navigation. We introduce Sound Spaces Audio Simulator, which enables realistic audio rendering for habitat. We also create a benchmark suite of tasks for audiovisual navigation to facilitate future work in this direction. Code and audio simulation data is available at our project page. Thank you for listening.